Hello viewers and welcome to another episode of Space Science with Python. Today we will talk a little bit about orbital elements of our near-Earth object population that we currently know. So a few thousands of NEOs. I think it was around like 30,000 or so. And before we start, I would like to say that, well, I will try to compress the information a little bit more in my videos. So I got some feedback that the videos are quite interesting for you guys, but most of you are more like not really beginners, but more of intermediate programmers, and it's sometimes a little bit slow also from the information density. So I will try to pace up things a little bit so that you will not get bored. So I'm trying to compress everything under 10 minutes, let's say, so that you can dive more into the code, and with this video you will just get the spirit, what was the idea, and then based on the script you can play around a little bit in your free time. So today we will talk about the orbital elements, and we will not use matplotlib today for plotting purposes, but we will use another package I will just show you just in a moment. But before we do this, we need, of course, our data. The data is, of course, in GitHub, so everything is uploaded there, as well as the script of today's session. And the first modules, well, it's quite simple. We have to load our data. I just see here cell number 16. It should be number 1. The kernel must be restarted, so everything runs from scratch. So we just import SQLite3, we assess our database, we then select here all our data from our database with this simple SQL command. It's really not black magic, and we use pandas for this. And now here in cell number 4, let's take a look at our data. So again, as I said, around 30,000 rows or 30,000 NEOs respectively, with the column's name, with the epoch, the semi-major axis, all the orbital elements you see here, the absolute magnitude, which corresponds to the size of an NEO. Take a look at the video from last time, as well as the aphelion and the perihelion, and these values are the sun farthest and sun closest distance, as well as the NEO class. And regarding the NEO class, I did also a video in the past. I think it was the second video or so, about where we talked about the Amors, the Athens, Apollos, Atiras, and also some outliers. Now let's move to cell number 5. And today we will use we will not use matplotlib and do some highly customizable functions, plots, but we will use Seaborn. And I don't know if some of you already know Seaborn or not. Seaborn, the link is in the description, is a library that provides us really nice and cool ways of plotting our data. So we can create, for example, this, like the scatter plot here, this example, the gallery. For example, this two-dimensional scatter plot with a histogram, two-dimensional histogram, and then with kernel density estimations, and then the contour lines. And this can be done only with a few lines of code. So this is really cool to create very sophisticated plots based on a pandas data frame. So it really extends the functionality and the capabilities of matplotlib. So there's a lot of things here to take a look. So I really encourage you to take a look at the Seaborn. I don't know if some of you of today's video know already Seaborn. We won't cover all the plots here and all the topics. We will use something something from the Seaborn library to get a really quick overview of our orbital elements. So it's not a plot that we will use, or you could use for a paper or something, because then we of course need some style adjustment and designing and so on, but we will really just use it for the sake of getting an insight into our data without playing too much around. So it's simply sometimes only one line of code with a few arguments, and then we plot everything and we are done, and then we can interpret the things. So this is the idea of today's session. We take a look at the orbital elements, interpret the data, and we will also later in the conclusion talk about what are the next steps. So why did we take a look at the orbital elements in the first place? Oops. So let's move back here to our new orbital elements. Now in the 5th row, we can now simply install Seaborn. I uploaded also a requirements.txt that contains Seaborn. Otherwise, you can simply write pip install Seaborn. So cell number 5. And then in cell number 6, we can, for example, create a simple histogram plot. So yeah, what we do is really we just call Seaborn, or I import it as SNS. This plot, then the NeoDF, and the x-axis is like the bins, and this is like the absolute magnitude. And then we can also clip it with a matplotlib command with xlim, and then you see we have here our result. So this is really cool, quite simple, and only with a single line of code. And of course, you can adjust this a little bit. You can say, I would like to have a certain number of bins or the bin width and so on. So I just wrote here a small comment. You can, of course, add a lot of different arguments here as an input to adjust the appearance of your plot. Cell number 7, what we are doing now, I would like to take a look at the histogram of the absolute magnitude, which corresponds to the size. If you recall, small absolute magnitude corresponds to a large asteroid and vice versa. So here we are plotting the histogram again in block number 7, but let's plot it and then I will explain it to you. So what did we do? First of all, I filtered out here all NEOs that are called others. So I just want to have the Amors, Apollo, Athens, and Arteras. We want to plot the absolute magnitude, and we differentiate by the NEO class. So this histogram here, as you saw it in block 6, here now in block 7, it's now differentiated in the NEO classes, and this corresponds to the 4 different colors: blue to Amor, orange to Apollo, green to Athens, red to Artera. Now you know Apollo, Amors, we have a lot of them, and Arteras only a couple, but you see the histogram here is, well, it's even larger than the other ones. That's because we use the probability statistics, so all bins sum up to 1, and we say that we do not use a common norm. So each individual histogram is, let's say, statistically decoupled from the others. So we norm each NEO class individually. And then we say also that the element step, so that we have here this step-like structure, and so we can take a look at this histogram. And with a bin width of 1, we bin the information also in 1 magnitude steps. And we already see some interesting stuff. So for example, Amor, Apollo, Athens, you see here some kind of distribution. We see a lot of objects with an absolute magnitude of, larger than 20. But here for the Arteras, we see that our distribution peaks or is distributed between 16 and 22 or 21. So we only know larger Arteras and not smaller ones. Why? Well, of course, observing Arteras is quite difficult because they are between the sun and the earth. So we do not see them in, let's say, a full moon state, because for this we need an alignment of the sun, the earth, and the object, the NEO. We only see, let's say, the waning or waxing moon-like shape or appearance of this NEO. So if you imagine something like a triangle, you know, the sun, the NEO, and the earth, and the sun illuminates the NEO, and we observe the NEO from some certain angle, we do not see a full illuminated disk, but more like a small shape of a scythe, right? So like Venus, for example. So we do not see the full illumination, so only partly illuminated. And since we can only observe these objects during dusk or dawn, we have also some kind of background noise from a brighter night sky, which means that we have a certain bias that it's easier to detect larger objects than smaller ones. So of course there are probably smaller ones, but we do not know them. So we did not observe them or discover them. There are for sure some smaller Arteras, but with our technological capabilities, we were not able yet to discover them. So this is what this small plot here implies. Let's go to the next plot, plot number 8. So let's plot it again. And what we did here is, well, I told this in one of the previous videos, that a histogram is quite nice and fancy, and you see here some kind of discrete structure, but what is the perfect bin size, right? And the perfect bin size, well, does not really exist. You can, if you have a too small, if your bin size is too small, you lose information. If it's too, if it's too big, you lose information. If it's too small, well, you may interpret there are some kind of structures or distributions that are not there. Yeah, so you have to be really careful choosing the perfect bin size. So there's this rule of thumb that you use the square root of the length of your array, of your data array, but that's just a rule of thumb. And the other possibility to create a distribution is replacing each dot here, each data point, by, for example, a Gaussian distribution, and then summing up all the Gaussian distributions to something called Kernel-Density Estimator. And this is what we do here in cell number 8. We create a displot. You see here again, we use the semi-major axis in this case. We differentiate by the neoclasses, and we do the Kernel-Density Estimator. Of course, the size, the width of the Gaussians is also depending on your information density and so on. There are certain information theoretical ideas how to adjust this bandwidth, also adaptively. But yeah, let's not dive too much into this. So we do this here, and then we also do something called stack. So all our distributions, the hull of this corresponds to our final distribution. And what we see here now is we have now here, okay, the Atiras, they are almost lost in this distribution. We have the Apollos in orange and the Amos in blue again. This is also quite nice here in Seaborn, that also this kind of ordering is preserved. So also here, blue, Amor were blue, Apollo orange, and so on. And what we see is that, for example, the Attens, we only know Attens with a semi-major axis between 0.5 and 1. Makes also a little bit sense if you take a look at the definition of the Attens, and here are the other ones. Now what we could do is we could now create a lot of different plots to see and check the different orbital elements, try to interpret them. But instead of plotting now thousands of different plots, Seaborn gives us some nice capabilities, and this is something I would like to show you in cell number 9. Now, first of all, we are filtering our NEO data. We say, okay, we ignore again our other data. We filter the semi-major axis, or we consider only NEOs with a semi-major axis smaller than 5 AU. And also the size, we focus on, let's say, mid-sized object and smaller objects, so between 15 and 30 meg. And then we filter also, we only consider the semi-major axis, the eccentricity, the inclination in degrees, the absolute magnitude, which is inverse connected to the size of the object, and the perihelion. And what we do here is we are creating something called a pair grid. So an n times n grid, and n is the number of columns of our NeoDF filtered data frame, which contains these orbital elements here and also the size. So we have a 5 times 5 matrix or grid. So in the grid, in the diagonal, we will have the histogram plots. We will have the histogram plots of the individual orbital elements, semi-major axis, eccentricity, and so on. And then we create two-dimensional plots, two-dimensional histogram plots and two-dimensional kernel density estimation plots in the triangle of the grid. So in the upper right corner, we create a histogram plot, two-dimensional, so it's here map upper, and in the lower part, we create a two-dimensional kernel density estimator. And now we hit run, so we create 25 images now, or 25 plots, and this may take a few seconds. So this is not really, it's a little bit, it takes some time because we have 30,000 data points to consider. So let's wait for a few seconds and then let's talk about the results. And we are back. We see now our 5 times 5 plots, and let's take a look at them, and let's be not overwhelmed by what you are seeing. So let's take a look at some of these crazy plots. So first of all, I would suggest let's take a look at the perihelion distribution. So the perihelion distribution you see here in the bottom right corner, we see that a lot of objects we observe have the peak, or the peak of the distribution is at around 1 AU. So not really surprising. I mean, that's what the name indicates, right? Near Earth object. So they are having their closest point here around at the orbit of our home planet. Some are a little bit more further away, and some get way closer to the sun than other objects. Now we can also take a look at some other graphs. Like for example, you take a look here to the left, the absolute magnitude on the x-axis and the perihelion in AU on the y-axis. So you see here this small grid, and again, a larger number corresponds to smaller object. And what you see here is a small little bump here, this little line. And what does it say? Well, it says that we see that objects that have a perihelion that goes farther away than 1 AU, so let's say 1.2 AU or even more, we did not observe any of them yet. So for example, here you see we have a lot of objects with, let's say, a absolute magnitude of 24 or 23. We already observed them, but an object with the same perihelion but a smaller one with, let's say, 30, well, we did not observe them yet. And that's not because they're not existing or so. That's because, well, we don't have the technical capabilities to observe them. We need maybe larger telescopes. Maybe they're difficult to identify or find, and so on and so forth. So this is quite difficult to they are quite difficult to find. And again, it doesn't mean that they do not exist or so, but it's quite difficult to really observe them. Also here the inclination, we see here an inclination distribution. So we see most objects, they have a prograde orbit. So they are revolving our sun in the same direction as our home planet does. So we see here 50 degrees, but however, this is really, really crazily aligned. So like 50 degrees or 45 degrees with respect to the ecliptic plane. So this is really, really huge. And of course, we can take a look here again to the size distribution with respect to other parameters. So what else can we do? For example, let's say, for example, let's take a look here, the absolute magnitude versus the inclination. We can also take a look at the kernel density estimation. So inclination here, the absolute magnitude is here, inclination is there. So we see here the distribution that is just a little bit rotated. And we see that we observed a lot of smaller objects with a smaller inclination, and objects with a larger inclination correspond to or are correlated with larger sizes. Yeah, so why do we see larger objects with larger inclinations and smaller ones? Are they not present? Don't they exist or so? Well, most likely they also exist, but since they have a very large inclination, their dwell time close to the ecliptic plane, maybe close to our home planet, is extremely short, and the time span of observing them really with our telescopes is so small that we did not find any of them yet, or only a few. So here's also some kind of observational bias. So the observational bias does not only apply simply for the size distribution, but it's also multidimensionally correlated with the orbital elements. So I encourage you to go through these plots a little bit and try to understand them and see what kind of biases you see there. And the original question of our project was, okay, what kind of observation strategy do we need to apply to find more objects? Yeah, so what kind of objects can we find here in this region? Are there any objects at all? And well, thankfully, we have numerical simulations, right? I mean, in our videos, I would like to show you also how to compute the brightness of an NEO and so on. But this is now the ground truth of our known NEO population. What we need now is some kind of simulation, simulated population. And thankfully, there is one. The most recent one is only 4 years old, from Grandvik et al. 2018. I will talk about this in the next video. We will download the data and take the same look. We'll take a look at the orbital element distribution and compare it with the NEOs from our NeoDice database that I just showed you here, and we will take a look at the differences, or we take a look at these NEOs that we did not observe yet. So where are they, or what is their appearance in the night sky? Are they even theoretically observable or not? So this is something we will answer in the future. So we will not consider the known distribution, but we will take the simulated distribution, let's say subtracted from the known distribution, and take a look at the unknown NEOs or potentially unknown NEOs, and then compute how and where should we look to observe them. And this is kind of nice science topic, I would say. It also, yeah, it's a little bit related to my bachelor thesis I did back in 2012. So I hope you're looking forward to the next video. And until then, take a look at Seaborn, go a little bit through the database, play around with the plotting. And since it's summer, again, next video is in 2 weeks. And I can only encourage you to also sometimes take a small break from coding and enjoy the weather. Talk to you next time and take care.